Record on this computer. And it should say that it's recording somewhere. It is. Okay. So we're doing, well, we're going to start with the basics. Basically, we start this course where any young child would start their educational life, mathematically that is. We start it with talking about numbers and their relationships to one another. Right? So we have numeration systems, you know, like we call them number systems, we call them numerals, we call them numbers. You know, these are things that we've been working with our entire lives. And so the reason we start at this point right back at the beginning is because they're things that we take for granted. Like we know what these mean intuitively. So to explain this concept to a person that's never seen or heard it before is not something that we would naturally think to do. All right. So, you know, just kind of, and it came up in conversation once. It's, you know, I think it had to be 20 years ago. I was interviewing for a job, and you know, there's some things that only come up when you're a teacher. But I was interviewing for a job, and the teacher, not the teacher, the administrator, asked me to explain in simple terms why multiplying two negatives give a positive. Okay? I didn't have any sense of what the questions were going to be going into the interview. I just knew that he was going to ask me some content questions, but that one caught me off guard because I'm interviewing for a high school math job at that point. You know, so I'm not thinking that I would even be teaching something along those lines. But that's the question he asked, and I failed to answer it correctly, or at least to his satisfaction, because he was playing devil's advocate. He assumed the role of, you know, a third or fourth grader, and said, I don't get it. Explain it a different way, please. I don't get it. I don't get it. I don't get it. And I was like, at the end, I was like, that's all I got, man. You know, and of course, on the ride home, I thought about 13 different ways I could have explained it so that he would have understood it, but it didn't come in the moment, you know? And so this is along those lines where we're trying to explain something that we generally intuitively understand, all right? So we know a numeration system, or like once you know a numeration system is the same as number system for naming and recording numbers, symbols used to represent numbers are numerals. Oh, okay. Yeah, so now you know what we're talking about. There's no further explanation required. However, for a young child, a lot more explanation is required, right? So I have the, you know, just a little bit of history of the origin of numbers, the tally and the Egyptian systems. All of this just boils down to the idea that it started off being more symbolic, and then it eventually had to become standardized. Right? Because if you do the tally system or the Roman numerals, at some point you got to say, well, I'm not just going to keep putting tally marks. So what do I do? Well, let me start clustering them together. You know, so instead of doing, you know, the 1, 2, 3, 4 as little dashes or whatever they're called, tallies, I mean, I guess. But, you know, we're doing it like 1, 2, 3, 4. The fifth one wouldn't just be a fifth one. Otherwise, what happens when you have to have 100 of them, right? So what we do is we do this, but then somebody was like, well, okay, that's all well and good, but what if I have 100 of these? I got to write this out 100 times? That's outrageous, right? So that's overly simplified version of the history, but that's essentially where it came from. Math and science always, without exception, comes from the need to solve some kind of problem. Right? We wouldn't have numbers if they weren't necessary to perform some kind of task. Right? So we get to the 10 for 1 principle. In a base 10 system, 10 smaller units are regrouped into one of the next larger unit. That's the system that we know and love. Right? Tens are convenient to work with, so there's really no pushback on that. You start thinking, oh well, why are we going to use this? Well, you want to group them by 12s? You want to group them by 16s? I mean, somebody thought that we should group things by 12s. Otherwise, we wouldn't have things like 12 inches per foot or 12 eggs in a dozen, you know? So there is a school of thought that allows for that. You know, like you could have the idea of sixteenths. Like who came up with that idea? Well, that's based off the idea that doubling values is a pretty convenient way of going about doing things. So, for example, if I was looking at, you know, so I'll actually just chuck it in here. Little side notation. Why not? Oh, I got to turn my pen on. That's one thing I got to get more and more comfortable with. Why not 16 for 1? Yeah. So it's a 10 for 1 principle. Why not 16 for 1? Well, the short answer to that is, well, if I got to multiply something by 10, that's not going to be difficult. I can multiply it by 10 times. All I'm doing is just tacking on more zeros at the end. If I'm going to multiply something by 16, that's going to get out of hand pretty quickly. All right, I got 16 by 16, 256 if I'm not mistaken. But then after that, it's like, you know, so, but what was the rationale behind, for example, when you look at an inch, you know, like when you look at a ruler and you look at an inch and those little tick marks that are there, there's 16 of them. Right? For the more precise, like rulers, like tape measures, that kind of thing, there's 16 little tick marks because it's broken up into 16ths. And the rationale behind that is, let me draw a little straight line segment here. Here's 0, here's 1. All right, 0 inches, 1 inches. So you're starting, then 1 inch later. All right. What somebody said is, okay, I got your ½ an inch right here. That's pretty easy. I could do a quarter by cutting that half in half. I can do an 8 by cutting that quarter in half. I can even go further. I can go a 16th. Now, of course, I run out of room here, but I can just kind of squeeze it in. That's the benefit of digital writing, because you can do stuff like that once you realize you're out of room. But, you know, you could also just write small too. So, you know, I don't want to spend people's money for them. So you get your 1/16 there, and at that point, people say, okay, that's precise enough. We don't have to go any more precise than that, because we're not going to gain anything from any more precision. All right. So when you start thinking of it that way, all right, it makes sense. You know, you check the chat here, because there's like a little pop-up now that comes up. It's kind of cool. It's just I don't really know the easiest way to navigate to the chat.
They're saying that they're students in another Zoom meeting. I guess they think that they're in our class, but they're not. I don't know if you have 2 links active.
Oh, this day is getting better and better. All right, hold on.
No, they're in the right class. They're just in a different Zoom.
Are they in a waiting room or something?
Yeah, it was 3 of us here, but I happen to get in now. Through my computer.
If you go to Blackboard and you click the link for like the class meet, yeah, when you click that, it just like rerouted me automatically to this. Like,
but
I'm not
you
even
have to have a Zoom account.
Oh, okay.
Oh, people are going through Zoom and getting stuck there?
I believe so.
Because I went through Blackboard.
It's asking for a password. That's why.
Yeah. Oh, okay. Yeah, that's the issue. You got to go through Blackboard to avoid the whole password thing.
That's what we did, and then when we the biggest is asking for password, but we manually put it into Zoom.
So, yeah, the rationale behind the value of having something being broken down into what they call base 16 is that it gives you more precision. You could have a base 32 where it's broken. Each tick mark is 1/32 of a unit away from 0. But we settle for a base 10 system because it's convenient. You know, the numbers are much more reasonable to work with. All right. However, you get to like the good old highways in the United States, and you see everything in miles per hour, and everything's in feet and miles and things like that. And you're like, oh well, this base 10 system is wonderful, but we don't use it. Everywhere else uses it for the most part. There's exceptions, but typically the base 10 system is considered to be the best way to go, right, for convenience. So just quick example. I'm trying to like scroll using a mouse when it's an iPad. So the students are typically presented examples such as the following when first diving into these concepts, and it'll say stuff like what number is shown, and it's really just to kind of get their feet wet. The idea behind this example is to help them develop a skill. Like, okay, I know that the long stick there is worth 10, right? Because it's a base 10 system, right? The other ones are 1. So this guy here is 10, and each one of these are 1. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 in all. So then they would say, like depending on how advanced they are and of what age group you're dealing with, they might say 10 plus 9, but they're probably saying something like, all right, I have 10 here, 11, 12, 13, 14, 15, 16, 17, 18, 19, and coming up with it that way. All right. So, but the bottom line is it's a base 10 system because after you get beyond the 9th value, if I threw another square there, right? So if I chucked in another square here, I wouldn't say 10 and then another 10. I would then graduate to the next 10 grouping, which would be 20, right? So, like they have different names, but it's still the same general idea, right? But this falls under the category of skill building. And in math, we want to focus not only on building skills, but getting at the underlying concept and developing fluency with the content, right? So and that's the kind of thing that like as students yourselves you can reflect back on, and you can tell when, especially in math, math is my worst subject, math is my best subject. Why is it your worst subject? Because of this. Why is it your best subject? Because of that. But for the folks who say it's their worst subject, it usually has to do with the fact that they have a pretty decent handle on the skills, but not the concepts. They don't understand the underlying concepts. They know what to do. They don't know why they're doing it, right? And the students who have a good understanding of the conceptual stuff tend to excel, right? Because they don't really have to focus on problem after problem after problem studying. They can really just take their time and say, okay, well, if I focus on understanding why it works, then I'm done. I don't have to study anymore, right? So I'll just read this blurb real quick, and then we'll talk some pros and cons. This is a good skill building example, but the prevailing wisdom nowadays suggests that students learn best when they're given tangible examples of the concept, so the real world examples. The common misconception is that these tangible examples must take the form of word problems. Rather, well-constructed games can be more powerful learning, can be a more powerful learning instrument. What are some of the pros and cons of this instructional technique? So when I'm talking about this instructional technique, I'm talking about the skill building, right? So in the case of the skill building, the pros are, and you could feel free to chime in on this. I'm still battling the whole, like, I can see my iPad, but now I can't see anybody else. So if you have a thought, just unmute and just chime in. But if you want me to just go for it, I can do that too. I'll give you one right off the top of my head, a pro related to skill building. And it's going to be very, I'll keep it simplistic. It's going to be, you can get stuff right on tests. So correspondingly, you have a con to go along with that. So yeah, you can get stuff right on tests. Are you going to get it right on all the tests? Every test that you take from there on out? You don't understand the underlying concept. You just know how to follow the steps. Step 1, step 2, step 3, circle your answer. You're going to have issues with retention.
Mm-hmm.
There have been plenty of studies over time related to intelligence and knowledge retention, but they're also inconclusive. That there's so little in terms of tangible data that you can fall back on, but you can get at the underlying theory, and that is, if you don't, I don't want to say the phrase that I'm thinking, but the information, if it's not made use of, it will eventually be lost. Right? So, just think back, different age groups in this class. Some people, high school was a few months ago, and some people, high school was a bunch of years ago. Right? If I asked you just off the cuff, if I said factor this polynomial, like I wrote a polynomial out and I said factor this polynomial, I'm going to have a wide variety of students with the ability to solve that problem, right? And that could be related to this idea of retention, right? So we have the skill was built when you were a freshman in high school or sophomore or whatever it was. You learned how to do it. You studied it. You maybe even went to extra help. You got a tutor. You did everything you needed to get through that test. You took the Regents exam at the end of the year if you were a New York State student. And you did fine on that. But now enough time has gone by that you just don't remember it anymore. That's part of it, because you did not retain that knowledge. But if you can get to a point where you're understanding the underlying scheme in a concept, then retention issues are reduced. All right. So another pro of building a skill would be, well, math, it snowballs. All right. And so what I mean by that is you take a concept from earlier in a school year or a semester, you'll learn how to do material related to that concept. And then later on, you build off of that concept. And you end up using that to solve another type of problem. So it's not the end all later on, it's just another step along the path. But it's a helpful resource in problem solving. Which has a C. All right, and so the associated con related to that idea is, if you never understood the concept to begin with, how do you know when to apply this skill? I just want to get a decent zoom here. Zoom within the zoom. That's like 4 zooms. So what you call it? The moral of the story here, I guess, has to do with applying, your own experiences. I kind of look back when I see students that, and after 20 years, I think I know everything, but I'm always surprised at the things that I discover along the way. I am almost 100% certain when a student struggles with word problems, that it's because they've always focused on the skills and they never focused on the underlying concept, like why it works the way it does. Okay, so just food for thought, because if you develop that mentality in your instruction, then it kind of feeds upon itself. And you find yourself as a teacher, you find yourself mastering material that you didn't quite have a solid handle on way back when you were learning it. Right? And so basically, if you're the person who says every time you see a word problem, I know what to do when I have the equation, I just don't know how to get the equation, then I'm probably talking about you. You know, so that's part of the challenge, I guess. Those are just two pros and cons that come off the top of my head. There's more, you know, because when you think of something like skill building, it sounds like a positive thing. What we're really looking at here is strictly emphasizing the skill building, right? So it's the difference between tutoring and teaching, right? And the reason why you take a class like this and other education type courses is because you want to teach, not necessarily tutor, right? Tutoring is all about the skills. You need to get stuff right on the test. That's what I'm getting paid for. I'm here to help you get stuff right on the test, right? I'll look over your homework if that's what you want. It doesn't matter, right? The teaching has to do with the underlying meaning and the thought. And it also comes down to, or comes back to, harkens back, if you will, to moments when you were sitting in class, when the teacher is explaining where a formula came from. He's like, oh, and here's the reason for this formula and this formula, this formula. And you're like, wait, if I just have the formula, don't I just plug the numbers in and get the answer? So what's all this other nonsense that you're going on and on about? They're trying to get at the underlying concept. Whether they're doing a good job of it or not is a different story, but that's what they're trying to do. Right? And that's, I guess, what I'm trying to do right now. But it is what it is. We do what we can. Okay, so that's the first page. So then this strategy, this one, yeah. I'm just curious. I want to try something real quick. No. The actual file has the link, but it's a funny clip. I think it might be worth watching. I just want to make sure I have the precise file up. Oh, that's weird. Okay. Okay, well, anyway, I'll talk about this. I'll find the clip in a minute. But I think I might have put it actually in our class video files. So that's something that's worth investigating in a few minutes. All right, so I saw that my son showed me a scene from Ralph Breaks the Internet, a post-credit scene. It was hilarious. Kids' movies are funny when they kind of throw in some just for the parents humor, but this one I actually lost it. Like, I was rolling. So anyway, I'll show the video in a few minutes. But a teacher presents the students with a pile of small but safe objects. The students may only use one index finger to count off the objects in piles of 10. All right. So I kind of like, I looked at this sort of like, and this is like an old school reference. I don't know how many people, package up the coins to bring to the bank anymore. But I used to do that when I was a kid, because it was like, okay, if you roll up all these coins, you get to keep the money. Right? So I had 5 siblings, and it would always be a battle to get to the quarters, because you wanted to roll up the quarters because you could have 10,000 pennies, but you're going to get more with the quarters. Right? So the object of this game is to collect the most piles of 10 in 30 seconds. For each set of 10 collected, you earn a tally mark. The student with the most tally marks after 30 seconds have expired wins. What are some of the pros and cons of this instructional technique? Right. So here, what I'm having them do is count off in piles of 10. So they have whatever the objects. Maybe they are pennies. Like if you have a ton of coins lying around. Now, I'm operating under the assumption that we're not in pandemic mode here, but you have a bunch of coins lying around, pennies, and maybe have the students bring in the pennies. You know, that's not out of bounds. You can do that. They may say no, but you can ask. So they bring in a ton of pennies, and you just want them to collect, to count off 10. You know, they only got 30 seconds, so they're not going to get through a whole hell of a lot. But they can only use one finger, so it's not like they can just like line them up with their hand and like, you know, just slide them on through. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they have to do it reasonably carefully because it's easy to fling those bad boys. All right. So for every set of 10, they get a tally mark. So they're going to compete with maybe it's groups of 2, groups of 3, groups of 5. It doesn't really matter. But at the end, somebody will have counted off more groups of 10 than others. This gets across the same skills as the previous example. That previous example came from an IXL practice sheet. And so, you know, in the spring, when everybody was in pandemic teaching, you know, especially in the high school, IXL became, in a lot of ways, the teaching. You know, it's like, all right, we'll do this assignment. You know, watch this video and do this assignment. That it's all skill-based. Okay? You're not getting at the underlying concept. But with this activity, you will drive at the underlying concept a little bit more than you would for that previous exercise, because you're not already given the cluster of 10. You have to create that yourself. And then an extension of this could be something along the lines of, all right, well, why piles of 10? You know, why not piles of 5? Wouldn't the game be easier if it was piles of 8? Sure. But now when I ask you, how many pennies do you have? You know, I didn't ask it in the setup here, but that's a follow-up to something like this. You say, huh, okay, Charlie, how many pennies do you have? And he or she comes back with, okay, I got 42. Well, how'd you know that? Well, I have 4 piles of 10 and I had 2 left over. I mean, he or she just figured out multiplication, addition, counting, grouping, all sorts of different skills related to this one concept, right? So sometimes a little creativity in developing your activities goes a long way, because you're hitting out a lot of instructional objectives with just one problem. And then you got to tie this back to the idea that it all started in my crazy brain with a freaking video in a kid's movie, you know, and that's how things happen. You know, sometimes you're observing things in real life and you're like, you know, that's an activity. Then you just jot it down and you go for it. All right. So we'll list the pros here. The pros are that you're getting at the underlying concept. And I'll pluralize it, concepts, because we definitely hit more than one concept here. Oh, my handwriting is brutal. Goes along with my psychosis. So getting at the underlying concepts. I won't go so far, because, you know, like one of the buzzwords in education now is engagement. It's an engaging exercise. Well, I mean, if we looked up the definition of engaging, there's nowhere in that term's definition where it says it has to be fun. It just has to capture their interest, right? So they got to be focused on the task. So it's an engaging, I guess I will write it in, but I'm putting it in quotes.
Mm-hmm.
It's an engaging activity, and I'm looking at that specifically because, like, they have to be focused on it in order to do it. You know, like, you give a kid 10 questions and tell them, okay, do these 10 questions, and then you can go for recess. All right, they're going to do the 10 questions, whether they're right or wrong, doesn't matter. They're not really engaged in that activity. Right? They're engaged in getting that activity done so that they can engage in recess, but they're not engaged in the learning. Here, you're tricking them into learning, right? And so that's where the engagement comes into play, right? So, sorry, question?
Oh, I said it's like you're forcing them.
Yeah, you're forcing them, but you know the games approach. You know, people want to play games. You got a choice in playing. I mean, there's some people right now in this Zoom, literally right now, that are playing games because that's more engaging than what I'm talking about. You know, and so now are they learning anything from that game? Maybe. I don't know if it's related to this topic, but you know, and honestly, it's not like I'm looking at people's screens or anything. I have no idea. It's just when you have 20 people in a class, somebody's got to be looking at their phone and be like, all right, well, these clans aren't going to clash themselves, so let me just let me get in there, you know. So that's part of it. But creating a game, even if it's not the greatest game in the world, it's still better than here, do this problem. Oh, you got it? Let's go over it together. Do this problem. You know, so there's a time and a place for that. It's called college, as you know, right? You know, it's like here, do these. Here, read these 50 pages by tomorrow and write a 10-page paper. You know, it's like they'll get that. At this point, it's the formative years. We want them to learn, and the best way for kids to learn is by captivating their interest. Okay? So, or capturing their interest. The cons, it's a process. You know, time, resources, environment. Environment's kind of a blanket catch-all, which I guess is what a blanket statement is. Yeah, I throw that one in there because it could mean so many different things. What I mean in this situation is I just gave you what I think is a wonderful example about how you could have all your students, you know, break up into groups, give them all some really filthy pennies, and have them count off in groups of 10, competing against one another, and like talk some smack to one another throughout the process, of course, you know, like however you want to do it. But they can't do that now because they got to be socially distanced 6 feet apart. So there goes that idea. But getting the wheels turning to start thinking, all right, well, this would be good if we were able to do it in class. What are some ways that I might be able to do this in class? And if not, what is an alternative to this that I might consider? Like, is there an online option? You know, like what are the possibilities there? You know, so that's another thing. There are a lot of apps out there that are just really simple annotation apps that don't even really involve, you know, paying anything, that allow you to just move something from one area to somewhere else. So, you know, there's options there. But, you know, as long as the thinking goes into, because really when you're teaching, the worst thing that you could do is embark on any kind of journey, whether it's an activity or a unit or anything, without having given it any thought. Because then what happens? You start working through it and you're like, well, that's stupid. Or the worst, wow, that only took 2 minutes. What am I going to do with the other 38? You know, so that's also part of it. But you know, that's a different story for a different day. The time management is really that's where teachers, I think, kind of earn their keep, being able to calendar and schedule everything out. So when we start talking about concepts as opposed to skills, you might think about a term like a cardinal number. Now, maybe you wouldn't intentionally think of this term. I almost said nerd. That's weird. You wouldn't necessarily think of the word itself, but you might think of the underlying concept. Right? So a cardinal number is a number denoting quantity. And an ordinal number is a number defining a thing's position in a series, like first, second, third. Yeah, so like these are things that we intuitively, we tend to understand. You know, like if I were to say, for example, how many students there are there in a class, I don't think people are going to say 15th as an answer. You know, what what comes after the 14th term, then you would say something like the 15th. You know, so these are things that you wouldn't define for your students. You wouldn't, like in a second grade class, if you wrote notes on the board, if you even have boards at the time, you know when you're in the front of a class, if you're even in the front of a class anymore, but you wouldn't be asking them to memorize that term. Yeah, maybe 30 years ago, sure, 30 years, maybe 40, 50 years ago, that would be something that you needed to define and know the definition of. But now it's just, do you understand the underlying concept? So as a teacher, you just want to take into account that there are these two different types of numbers or ways of representing numbers, and that you need to hit on both of them when you're creating your examples. Okay? And so when you look at it that way, it's pretty straightforward. And those are things, you don't make a lesson, you don't make an entire lesson to address cardinal numbers and ordinal numbers. Those are things that you work on throughout the day. You know, you're in a third grade class, you're going to have different periods of time, and math doesn't have to necessarily be limited to math. You know, so when you're putting the kids in groups, you have them count off 1, 2, 3, 1, 2, 3, 1, 2, 3, you know, and so that all the ones get in one group, all the twos get in another group. So you've just addressed both the idea of cardinality and ordinality. You know, so you're kind of hitting on it in that regard, and you're developing an intuitive understanding of it. Right. So part of the challenge is not, and this is not music to state education department, and NCTM is the National Council of Teachers of Mathematics. That's a thing, if you didn't know. What I'm about to say is not music to their ears. They give, or they publish a list of standards that need to be addressed. New York State takes it a step further and makes they call them modules, if you haven't heard of those terms yet. And what some teachers were doing when Common Core first came out was they would just go onto the Engage NY website and just print out all the modules, and that would be the notebook or workbook for the students. And you know, they did that because it was like, well, you want us to do it this way, we'll do it this way. And there was pros and cons to that approach, mostly cons, but you know, like that was the option that they chose. I looked at it a different way and said, okay, well, you gave me this list of topics that needs to be covered, or that needs to, yeah, I said it right. It needs to be covered. This doesn't deserve its own lesson. Cardinal numbers, ordinal numbers, that doesn't get its own lesson. That's part of everyday life. So that comes right out. That doesn't get, we don't teach a Common Core lesson about that. We just interact with our students, and because we interact with them, we get across the concept of cardinal and ordinal numbers, right? And as a teacher, you can assess informally, but still come up with the idea that a student meets the standard. You can say, okay, yeah, we didn't take a test on cardinal and ordinal numbers, but I remember at least 3 instances where you demonstrated your knowledge of those ideas through activities. Maybe it was even in a gym class or something like that. And because of that, I can now check you off as having, you know, at least, I wouldn't say mastered that concept, because mastery is a different animal altogether, but yeah, like we could say that you're effective in that category. Yeah, so the moral of the story here is, yeah, we got to get at these ideas, but we don't have to teach them directly every single time. The names of the base 10 units, that is something that we do have to teach directly. Otherwise, we have students saying things like gajillion, all right? And so that's not a number. We want them to at least know what the numbers are, and if they want to be silly and say bazillion, quadrillion, or whatever, and make up some terms, that's fine, as long as they really truly understand the hierarchy, right? So we're going ones, tens, hundreds, thousands. We're always multiplying by tens, And so there is that convention, that naming convention where, you know, like the lower ones are always a little iffy, you know, like the ones that tens, it's like, it's the ground level, you know, but then once you get to the higher levels, you get, you know, the 1,000, then 10,000, then 100,000. Then we move on to the next name, million, 10 million, 100 million, then the next name, billion, 10 billion, 100 billion, then the next name, you know, and so we go from there. As long as you have a sense of the naming convention, then you have the idea down, all right? So that's part of it, but it all comes back to the groups of 10. All right. So on the previous page, when we were talking about, well, why not have a base 16 system or a base 32 or base 8, base 2, base 4, whatever? Why does it have to be a base 10 system? All of our numbers, or at least the way we know numbers and numeration, is based off of that naming convention. All right. So you have an example here. It doesn't look like it fits any of these ideas, but this is a typical second, third grade type example. What's the sum of 7 and 5? Justify using a diagram. Now, the last part isn't typical of the second grade or third grade classroom. That's for us. What is the benefit of asking the students to use a diagram? You know, so we could actually tackle that part first. You're getting at the different modes of learning. So it addresses different modes of learning. Okay. Now that's different from learning styles, right? Because I remember a long time ago now taking a psychology class, and I think it was psychology, but the first thing that we had to do in the class was do a learning style profile or learning style inventory, I think is what it was called. And like once you've done that, you know, you answer a bunch of questions and you take the sum of the values in this category and that category and that category, and depending on what the numbers were, it put you in a particular way of learning. So you're a visual learner, or you're an auditory learner, or you're a combination of the two. You know, that's not this. The different modes of learning that are specific to math are really just boiled down to three basic ideas. One is that, and I'll actually just jot them down here. I formally address them later on, but might as well get them out of the way early. Computation, visual, and verbal. All right, so computation, I think that one is clear. Like that's the number crunching, the act of adding two numbers. The visual, it could be a graph if you're thinking in terms of like you take it like a college algebra class or something like that. You did a lot of graphing there, so it could be something along those lines. But it could be something as simple as a number line. Okay, and in this case, I left it open-ended on the diagram. What kind of diagram do you want to use? I'll show you a couple of different varieties. I'll show you the one that I would have used if I were the student, and I'll show you the one that I saw my son using. So, because it was kind of interesting, and I thought it was different, so why not? And then the verbal is the explanation, right? Because, you know, like it's kind of weird to think about, you know, 'cause when I first started becoming, you know, going through the process of becoming a teacher, they were very big on journals. They wanted teachers to require students to keep journals, specifically math journals. And it was supposed to be like, you know, a really deep dive into their thinking about the concepts. And it almost always ended up being this stuff is really hard. I don't like it. You teach too fast. You teach too slow. I don't think I'm ever going to learn. It was never anything like, one interesting thing that I learned today was that, like if I take part of the 7 and transfer it to the 5 or vice versa, that can make it easier to have these two things together. It was never like that. And so it kind of went out the window, but that's what they were trying to drive at. And a lot of the things like policies and procedures that get implemented, they're almost always to drive at what are supposed to be really well thought out or even noble goals. But they get bastardized, and because of that, we end up with Common Core. So this idea is, when we talk about using the diagram, it's to get them to access that part of their brain and help them to internalize it for the purpose of retention. All right. So by hitting on these 3 different categories, we're hitting on different aspects of the brain, allowing them to develop long-term retention. All right. So here's where my brain would have taken me if I were the student. So I got a little number line here. Now you could, the sum of 7 and 5 is, as long as you know sum means add, and that's another conversation, vocabulary. You can figure this out. You do it in your head. You can get a calculator. It doesn't make a difference. This is to get across the idea. So 5 more. So I put 5 more tick marks. That's going to get me 6, up 6. Geez, I'm batting 1,000. 8, 9, 10, 11, 12. All right, so this is my 5. And this is my 7. Now, don't get me wrong, as a 2nd grader, 3rd grader, I'm not putting this much detail. I'm not color coding it. It's going to be a sloppy mess, but it wouldn't look too different from this, except, obviously completely messy. Now, this is what my son did. And this is the way his teacher wants him to do it. And this is pretty typical nowadays. And it's a good technique, so I'm not bad mouthing this technique. So you got 1, 2, 3, 4, 5, 6, 7.
Yeah, that's how I would have did it.
Yeah, so you got your 7, right? So then from the 5, so I got this squared away. I got my 7 accounted for. I want to do that in red, actually. I'm going to snag 3 from here, and that's going to leave me with 2. So that's going to make my 10 group. And then I'll have 2 more. So I'm going to take the 7 that I have. I'm going to use what I have from the 5 to get me to the 10 block. And then whatever's left over, I just tack on at the end. So now I know it's 10, 11, 12. There it is. All right. So pros and cons either way. The big pro to either of these techniques is that you have visual representation. Now, depending on the quality of the visual, it may or may not be easy to make heads or tails of what the reasoning was behind it, but there's a justification there, so that's fine. The big con to any use of a diagram, if you leave it open-ended, is that you could get a whole lot of stuff that you weren't banking on. And as a teacher, early on, in the early days, it was like, all right, well, I came up with 5 different possible ways to answer this question. Your answer doesn't look like any of it, so it must be wrong. And then you conference with the student and you hear their line of reasoning behind their work, and you're like, oh, not only is that right, but it's better than the way I was doing it. And so you got to withhold judgment just because something looks like a hot mess on paper doesn't mean that it's incorrect. All right. So that's one of the, you don't want to go red pen crazy. You want to just kind of restrain yourself, because odds are there is some knowledge that's being addressed. The only time knowledge is not being displayed on paper is when they leave it blank. You can always glean something about what the student is thinking based off of what they produce on paper. Now, it may be that you're gleaning that they're thinking that this is a different question because this isn't even close to right. But there usually is some evidence of thinking, and if you can kind of dive into that, you can get a sense of where they're at. You know. So the next up is whole numbers. That goes pretty quickly, even though there's a whole lot of writing here. But what we're going to do now is take a 10-minute break, and then okay, so yeah, now we're going to take a 10-minute break. So at 7:30 we'll come back and resume. So yeah, like I mentioned last class, I think I mentioned, my classes are melding together here. We're going to go until whatever 30 minutes before the end of class is. That's when class ends and the individual extra help session begins. All right, so the Q&A portion of the class. So I think this class, what does it end? 8:50? Well, whatever. I'll look it up. It's 8:40 or 8:50. I can't remember. But so at the 8:10, 8:20 mark is when we're gonna be in, and that'll be on a weekly basis. All right. So we're taking our 10-minute break right now. Resume recording. Resume. So, history of whole numbers. I mean, there's a whole blurb there. I mean, I tried to get a little bit of the history involved wherever possible, but I didn't want to overdo it because when that happens, it's very easy to lose people. I had to take a history of math class back in the day, and it was not fun. It's just at a certain point, you just want to get on with it, you know. And so this stuff that I have here, or at least I try to in all of my notes, they kind of fall under the category of like fun facts, you know, like, hey, you ever wondered where the whole numbers came from? Why do they call whole numbers? You know, that this gives you a little bit of a sense of it so that you can feel comfortable if somebody were to ask you the question, you know. And as a teacher, and I'm sure you've heard this one before, it's all right to say that you don't know something. I have colleagues that, and whether it's high school, college, every stop that I've made in my career, I got ones that are very quick to admit that they don't know how to do something, and I got ones that'll never admit it. You know, and it's just, that's just how it is. People are different. You know, I kind of fall somewhere in between, where I feel like if it's something I should know, then I'll figure it out on my own, rather than admit that I wasn't paying attention. But if it's something that, you know, like this looks like it's complicated, let me get some insight from somebody. That's usually when I chime in. But this is stuff like, if a student asks you, hey, so the term integer, where did that come from? It's all right to say, I have no friggin' clue. I mean, it's not all right to say it that way to a second grader, but third grader or whatever. But you could get across the idea, you know what? I don't know. Let's look it up. You know, that's part of the learning experience too. You're allowed to learn stuff also. Right? So one of the things that people have struggled with, and it's not just in the elementary level, it's all the way up, is the concept of zero. Because zero can take on a lot of different meanings. And one of those meanings is the idea of emptiness. So, you know, like when you're explaining it to a little one for the first time, you know, which of the following circles contain 0 dots, what you want to do is you want to be very explicit. You want it to be very clear what you're looking for. You know, it's not the time when you're first introducing this concept of zero. You don't want to get involved in vagaries. You want to nail it down to simple tasks, like a to-do list. All right, which one has no dots? All right, that's easy. And you want them to say that. You want them to be like, that's an easy one. Okay, that one has no dots. Okay, how many of the following circles contain 0 dots? All right, so different question. right? So we're also getting at the idea of ordinality and cardinality here. So without ever having introduced that term to the students, they now have to recognize that there is one circle that has 0 dots in it, right? So it's the same, it's referencing the same circle, but it's asking a different thing, right? So in the first, I mean, I just highlighted it, but to be appropriate, I should probably use the ordinal terming here and say that the first circle. Whereas the second question is the cardinal value. But again, you never have to mention those words to the students. You just want to have it in your mind that these are 2 different ways of looking at the number. How many dots are in the first circle, still referencing the same circle. There are no dots in that circle, right? So again, by asking the question in these three ways, we gauge true understanding, but we risk confusing them because we're hitting them with the same question that looks very similar, has a lot of the same words, questions that look very similar, have a lot of the same words, but they're asking for 3 very different things, right? So there's that part of it. But if you're explicit in how you ask the question and you're careful not to cut corners in your verbiage, then you can get the job done. It's, I mean, I don't know how many of you have your own kids or a younger sibling who's going through elementary school now, or if you have any kind of memory of elementary school in recent years. But the big thing is like the parents trying to help the kid with the homework and the parent can't figure out what the hell the question's asking. That's really what's happening in a lot of cases, because poorly phrased questions don't allow the student to comprehend what is being asked of them. They may very well understand the concept, they just don't know, they don't know what they're being asked to do, right? So being more explicit with your phrasing can allow for that to happen, right? So here, and also we're getting at the idea of 0, emptiness, in 3 different ways, and how sometimes the 0 concept can lead to an answer that's not necessarily the number 0. Right? So all these things are baking in this kind of environment. Something else to consider, and this is you know, this is beyond the scope of the course, and this has to do with just organization and strategy. Copy paste. Yeah, it's the same diagrams. Phrasing of the questions are relatively similar, but the diagrams. One of the biggest challenges as a teacher is the creation of unique examples. The idea that you could use the same diagram for 3 completely different problems, that's a good thing, because if you're thinking in terms of like, okay, I want to put this question on a test, but I need to have 3 different versions of that test. You know, like I like to have 2 different versions in the class, and then I want to have 1 makeup version. You know, now I have 3 different problems. Yeah, they're assessing different things, but that doesn't matter. You don't have to assess the exact same stuff on a test, right? You just have to cover the broad scope of concepts that are in the unit, right? But that could be something that factors into your thinking. You got a nice looking set of diagrams here. Why not see what you can do with them? And there's nothing to say that you can't switch it over and say, you know, which of the following circles contains exactly 1 dot? Or now you can start, if you, for the higher level kids, you could start getting into at least and at most, right? Has at least 1 dot, at most 2 dots. You know, you can start playing around with it. Same diagram, but you can get like 100 questions out of this, right? So, and all pretty easy to grade too. That's the other thing you want to keep in mind, right? Number lines, also very important. They get a bad rap. Number lines and graphs, I mean, they get a really bad rap in education from the student perspective because of the way that they're implemented. Because most of the time when you're asked to create a graph, it's usually as an add-on. It's like, okay, solve this problem, and oh, by the way, also, you know, while you're at it, make a graph too. You know, we got just make a graph. We'll do that also. You're like, oh, that's great. But you never really get at why you're making the graph. Here we're using graphs, whether it's a number line or a two-dimensional graph, in forming the solution to problems rather than just being a tack on at the end. All right. And that's the same for even, you think about statistical displays, like a bar graph or a pie chart or something like that. Like as a student, it's always like, find these values, run these calculations, do that, and oh, by the way, make a pie graph. You're like, okay, fine, I'll do that. But really, if you think about it, if you're reading an article online and it's something relevant to your interests, you know, you're learning about current events or politics, you know, like whatever, it doesn't even matter. You see all of this data. Somebody conducted a study. They think that this group is they're getting a bad rap, you know? So they get all this data and they list it all in the article. They reference it. They talk about all these complicated, convoluted stuff. As a reader of that article, you're like, just show me the picture. Like, I don't want to see all these words. Just show, oh, the pie chart shows me everything I need. You know, like, why do I have to read this whole freaking thing? Like, just show me the picture, you know? So that's the mentality that we're trying to develop now, where it's like the pictures shouldn't just be a throw in at the end. They should be formulated as a useful tool in helping explain what it is that is, you know, you're trying to explain. So number lines could be a useful tool for developing a deep understanding of whole numbers. Okay, I mean, probably overselling it there, but we have to consider cardinality and ordinality when making use of these devices. Make it sound really fancy. Plot the numbers, plot a point on a seventh value and label it A. So not anything overly complicated. The seventh value. So 1, 2, 3, 4, 5. Oh, that is the seventh value. I just wanted to make sure because I wasn't really reading it. And then plot a point on the number 7 and label it B. So same point, but we're calling this B also. So this is an example of where cardinality and ordinality would yield the same result, right? But that's only because that number line started at the number 0. If it started at anything else, different story, all right? I honestly can't remember. I thought I had another example here, but it doesn't look like I do. So you know what I'm going to do? I'm going to get cute here. I'm going to create a new example. Let me get rid of this. Cut. Take a screenshot. Save image. Put this back. And paste. That's another benefit of these digital writing tools. This time though, I'm going to get rid of the 0. There's no 0 there. So in this case, so same problem, but new number line, right? So there's no 0. So the 7th value, so 1, 2, 3, 4, 5, 6, 7th value would be A. But still, the second part is then plot a point on the number 7 and label it B. So here's an example of how they would be different. All right. And you know, it's something that, again, it's not really for you. You know, like the content instruction. I'm not showing you this to teach you something that you learned back in 2nd grade. I'm teaching you something so that you could then turn around and teach it to somebody else. All right. So it's accounting for the different varieties of a problem. Because if I just left it at that first example, and I honestly, I don't even know what happened. I think I'm missing a page in this file. But if I just left it at that first example, that wouldn't have got the job done. They'd be like, okay, noted. 7th and 7 mean the exact same thing, you know? But then if I only went with my second version of the example, then they'd be like, okay, there's never a circumstance in which the 7th value will be the number 7. So they would get the wrong or an incomplete understanding in that regard also. So by showing both cases, they're like, okay, so sometimes it is, sometimes it isn't. So why did it work in the first case and why did it not work in the second case? And by work, I mean end up being at the same location. And that has everything to do with the number 0, right? So that's where the conversation begins. It's like, okay, well, we're starting off with the number 0. So the 7th value away from 0 is the number 7, right? But the 7th value away from 20, you wouldn't expect that to be 7. A 7th value away from 100, you know, that wouldn't be 7. So it depends on where your starting point is. If your starting point is at 0, then the value, and you're assuming that you're going to the right in the positive direction, the 7th value and the number 7 would be the same thing. All right. So, you know, it's little things that you understand intuitively, but you would never really think, I really gotta spend some time on this. You know, I want to make sure my students understand this concept, because it's not something that you think that, like going in, you would think that they would necessarily need extra time and care in order to help them understand, but they need a ton of it, you know? And so that's part of it, I guess. Yeah, so that's lesson 1.1. So we're gonna hop over to lesson 1.2. This one is quicker. You know, I mean, there's a lot more diagrams, but it goes quicker. So, and we'll finish up class on this document tonight. And like I said, you can get the blank ones and you can work along, or you can follow along and you can get the stuff later. You know, it's all up to you. I let you decide. Well, I take a sip of my wool tie. So next up in the conversation is decimal numbers. So we've talked about whole numbers, and really what we're doing is we're building outward towards the concepts that exist related to the real number system. All right, so you got your whole number. You start off with the counting numbers, and you throw in zeros, so now you have whole numbers. Now we're throwing in the values in between the whole numbers. Okay, so fractions, decimals, things like that. All right, this blurb here in the beginning, fractions and decimals historically arose out of a need to express values that were not whole number quantities. If your answer to where did this come from, why was it invented, is because there was a need for it, then you're not wrong. That should always be where your thinking takes you first. For math and science, there was a need. This was developed in order to fulfill or satisfy that need. All right, and it comes from the fact that, okay, I got a field full of crops, and well, I'm not going to use it all, so I'm gonna sell some of it, but not all of it. Am I going to say that I'm going to sell 15,000 ears of corn, or would it be easy to say I'm going to sell half an acre? You know, like whatever the dimensions or the measurement used to determine the size of your object. Like, I'm going to use a half. I'm going to sell a half or a quarter or 3/8 of it, you know? So that's the real thinking there, right? Several ways you can view the relationship between the two terms, and this is where things get a little dicey. Right? We say decimals are a result of division operation implied by the fraction form of a number. All right, so here's my basic example. 2 slices of a pie containing 8 slices of equal size are removed from the pie. All right, so you have a standard pizza, and you're removing 2 slices from that pie. All right, so what fraction remains? Well, you took 2 away, so you have 6 out of the 8. All right, So then 6 divided by 8, you get 3/4 or 0.75. We'll get into the skills associated with the zooming is going nuts on me. It just takes on a life of its own. We will get into like the mechanics and the pedagogy behind actually dividing later in the course. But for now, we're just going to assume that the answer was either given or easily obtained. All right, so we got 0.75. So I'll read this blurb too because it's kind of important. Using the base 10 system, decimals are created by establishing places to the right of the ones place. We indicate the location of the ones place by placing a decimal point to its right. A little something in the way there. Starting at the ones place, we divide the unit into 10 equal pieces to create a new unit known as a tenth. Right? And so some people go through your entire life and have no idea why those values after a decimal point are called what they are. So this is the rationale. You're taking one whole unit and splitting it up into tenths. That's where the term tenth comes from. So if you were to take that one whole unit and split it up into 100 equal pieces, each one of those pieces would be 1/100th of the original. Tenths are recorded to the place, or in the place to the right of the ones place. Then we divide a tenth into 10 equal pieces to create a new unit known as 100, and so on. All right, so we can keep going with that process to get thousandths and 10,000ths, 100,000ths, and on and on and on. All right, so to conceptualize to a young one that 0.75 or 75 hundredths or 75 over 100 is the same as 6/8 or 3/4 can be very tricky. I mean, some people like stopped being good at math when fractions were introduced. Right? That's part of it. It's a conceptual understanding of it that caused that to happen. Right? So we would typically want to start with an example that's somewhat more number friendly. So we don't want to jump into a 0.75 because the student's going to be like 75 out of 100, but I only have 8 slices. So I got to break my pizza up into 100 different pieces, and then that 100 different pieces, I'm going to collect 75 of them. That sounds complicated. And then you start getting into, well, what about the width of the pizza roller? Like you start cutting it, you're going to lose some pizza that way. Like that's a lot of pizza that you're sacrificing for those tiny slices, little slivers. So the better example to start off with, 4 slices of pizza containing 8 slices are removed from the pie. So 4 out of 8 remain. Four out of 8 is 0.5 in decimal form. Now, 4 out of 8, okay, so we still have a conceptual understanding of what 4 out of 8 looks like. Here's 1, 2, 3, 4. That's half the pie. That's easy enough. This 0.5 is the same as saying 5/10, or 5 of 1/10. Okay, or so 5 1/10. All right, so we're taking 5 of those 1/10. So what I did to help them conceptualize this is, all right, we'll take the same circle, same size, roughly. I mean, I ballpark it. Instead of cutting it 8 ways, let's cut it 10 ways, equal size. I did the work for them because, like they're in 3rd grade. I'm sure they could do it with enough time, but it would take too much time. All right. So now I'm going to show them that if I take 5 slices out of the 10 available slices here, that I'm going to get the same amount of the pizza that I did when I had the 4 out of the 8. So here's 1, 2, 3, 4, 5. Still half a pie. So in both cases, half a pie, it gets the job done. So whether you look at it as 4 out of 8, 4 divided by 8 giving 0.5, which is 5/10. 5 of those 1/10 of a pie, either way, you're driving at this idea of fractional equivalence, and also that there is a corresponding decimal related to that fraction. Okay, so that it takes some doing to explain this concept, but it's there, and the examples are there. Pizza's the go-to. You're really, I mean, it doesn't have to necessarily be pizza, I guess. Any kind of pie, you know, it's a circular figure sliced up. You know, you could even bring in a pizza and do it, but that, you know, pandemic teachings. And I suppose they could watch you eat the pizza over a Zoom meeting or something. That's probably what I would do. I would make my students watch me eat the pizza, like pizza. Went on a pizza tour recently. It worked out really, really well for me. Learned a lot of good pizza joints in the area. So far, my go-to is Nicky's for the Sicilian, and we like Johnny's in Mount Vernon for the for their signature pie. But next up is Capri in Yonkers. So I haven't tried that one yet, but I've been told that it's a very sizable Sicilian slice there, and it's very doughy and tasty. So I'm looking forward to giving that a shot.
I love Johnny.
Johnny's?
Yeah.
Yeah. Yeah, I got. We're due for another Johnny's run soon.
Are they open?
They are, yeah.
Oh.
Yeah, they asked us when we went there last. They're like, you want us to tie it up for you, or are you just going to eat it out in the parking lot? Because everybody was just buying it and eating it out in the parking lot. I like, this place is great. So, you see, we have the place value chart. That's all part of it. You know, like we investigate, we talk pizza, we create real life examples, but eventually they have to formally address the concept. Now here, we're not doing anything with rounding or anything like that. We'll take care of that next class. But at this point, it's just learning how to name the appropriate terms. So, and in this case, it's all a matter of just lining up the values based off of what you see in the number itself, right? With the decimal point being that line or point of demarcation, right? So, this is the tried and true approach. Is there a better way out there? I suppose you could sing them a song about the place value chart. I don't know. It seems like when in doubt, people make up songs for stuff. Show them a cartoon where the journey to create the place value chart. I don't know. Like, I'm not big on that kind of stuff, but like if you can get creative, that's good. But sometimes creative for creative's sake is you're kind of battling yourself there. You're defeating your own purposes. Here, it gets the skill across, but they have no choice but to acknowledge that there are names for each of these values as they're writing the numbers themselves. So we write the values appropriately, and in this case, and actually in each of these cases, we could write the number from right to left for convenience, but you can do it any way you want. 6, 2, 1, because again, the point of demarcation is that decimal point. 5, 2, 1, 3, 2. Two, 3. So, get the commas in, get the decimal points in. We have the values. You can fill out the rest with zeros if you want, but that's typically not the way we handle it. But now, with the place value chart, the student can look at it and say, all right, I got to read this off. What am I going to say? I'm going to say, well, I'm not going to say 3 10,000s. I'm going to look at them and say 3. Okay, so 10 3 times, that's 30. Right? So 32,000, 125, and so on. So they have a better shot at getting the naming convention down, but also they have an idea of what the place values are. And the consistency of it is important. The one thing that gets 10-year-olds, 6-year-olds, 50-year-olds, 70-year-olds confused when it comes to place values is these bad boys. It's just you expect it to work one way the way it works the other way. So you expect it to go to the right of the decimal the same way it goes to the left of the decimal. It just doesn't. Right? So you got to kind of look at the ones place and the decimal as sort of a package deal, because what's happening is you're taking when you're dealing with a decimal point, this is, and this for a lot of people is sort of mind-blowing, but also the first reaction that I usually get for people when I show this is, oh, it's overcomplicated. It's like you're making this more complicated than it needs to be. Sorry. But then right after they get over that, they realize, whoa, that changes everything. All of this, everything that I highlighted, and even beyond, is a fraction of 1 unit. Again, pardon the handwriting. It's a fraction of 1 unit. So everything that comes up to the right of that decimal, it's all adding up to, and it'll never get to, but it's approaching the value of 1. So just think about what the largest value after a decimal point could be. The best we could ever do is 0.9 repeated, which if you could ever get out to that last 9, when you're repeating all those 9s, you know, you're putting infinitely many 9s. If you can get to infinity and you put all that together, you would actually get to 1 whole unit. So collectively, all of these decimal values amount to a fraction of just the ones place. All right. So it's kind of like we got the 10,000s, the thousands, the hundreds, the tens. We got the ones, and then we have a little bit left over just from the ones place. So a little bit more for the ones, nothing beyond that. And that's where the tens, the hundreds, and the thousands come from. All right. So that's a tricky thing to wrap your brain around, because you're not taught to think that way. And what really makes it, I'll say interesting, but translation is absurd, is that you were never taught that way, but you're expected to teach it so that somebody else can walk away with that idea. You know, that's something, you know. So the next one, you know, it's really just, I mean, actually, I don't even know if I have enough places to fit this. This is a bad example. Yeah, anyone, so I'm just going to get rid of the 1, 2. Any one of these corrections, additions that I made to the notes, they all count as typos. So if you submit those on Remind, you can get a bonus point for each one that you submit. So take advantage. Again, it's first come, first served, though. I'll send out a reminder on that later. Better yet, I'll send up one when I fix Blackboard and all the nonsense there. I'll set it up so that there's a particular assignment related to just how to submit typos for bonus credit. 0, 0, 1. And then the last one is just 1.101. So really, it's just a simple task, but for something like this, it's the conversation more than anything else that's really going to get you where you need to go. I don't know how. Oh, pizza and brew. I agree. I do like pizza and brew. Yeah. I got the baked clams from there a couple months ago, and I broke out into hives. So I don't know if it means that I'm allergic to the clams, but they were so good. Or if maybe it was just a one-time thing. But we hadn't gone back recently, so it's on my list. I got to go back there. And it's right around the corner, for crying out loud. You know, you can't go wrong. But what I did, and it took a while because this is not something that I'm really that great at. There's some people that they can make animations, they can go crazy with this stuff. I can make lines, and I can copy paste and snip and stuff like that, and I can make some tables. So this is my contribution. But what I wanted to do is somehow get across the idea of what a tenth was really getting at, what a hundredth was really getting at. It's all one unit that's being divvied up by 10, by 100, by 1,000. The issue with this way of explaining it is after you get past 1,000, now you're getting into 4 dimensions. And I mean, to explain anything beyond 3 dimensions to even an adult is complicated, let alone a kid, right? So, you know, you could run into some territory where the kid's like, hey, what would it be like for 10,000? I think your answer justifiably would be, I would show you, but your brain is going to melt. And then they go home crying, and you've got a parent phone call on your hands, you know, so you just got to be careful about how you do things. All right. So, but yeah, trying to produce something in 4 dimensions is not fun, or at least not for that population. All right. So that was page 2. Representing them as length. So again, back to the number line, very important, because again, not only are we getting across the idea of value, but we're also getting across the idea of position. I found this link. It's linked in the PDF file. If you click on it, Zeno's paradox. It's pretty interesting. It's an old paradox. I mean, the link is pretty interesting. The paradox itself is very interesting because it's all theoretical mathematics. The gist of it is, if you needed to go from point A to point B, but you could only travel by covering half the distance between where you were and where you want to be, and you do that repeatedly over and over and over again, Zeno's paradox says that you'll never get there. Mathematically, you'll never get there. Right? You keep dividing by 2, you'll get infinitesimally close to your destination, but you'll never actually get there. Whereas, practically speaking, I'm at point A, now I'm at point B. I'm at point A, I'm at point B. You're going to get there. It's a fact of life that you're going to get to your destination unless there's some crazy obstacle in your way. Right? But Zeno's paradox is getting at the mathematics behind it, where it's like, well, if you're always cutting your distance in half, you're never gonna get to the distance between the 2 points being equal to 0. So obviously you don't start off with that example, but that could be a nice extension problem when you're dealing with a group of kids who are just learning this skill, where you say, okay, here's the idea of Zeno's paradox. You have point A at point, it's 0 on a number line, 0 to 10, for example, or maybe even 0 to 100 like we have here. So you got to cover a distance of 100. So you make a mark at 50, then you make a mark at 25, and you keep going. When will you get to a 0 distance? And their answer would be, well, according to my calculations, never, but I know I can. All I got to do is walk, you know? So, but yeah, you're probably going to start off with something way less complicated, like plotting 1.46. Now, this is a good example because it gets across the idea not only of the value of a number, but also the scale factor of a number. It also has a slight conversion, but the conversion isn't complicated. I mean, it's complicated to anybody who's never seen a fraction before, but we're assuming that this example is given to somebody who maybe has gotten a little bit of experience. So 1 5/10. So we talked about this on the previous, or 2 pages ago. 5/10 is 5 of those 1/10. So you can look at it that way, but it really amounts to 0.5. All right, so we have a 1.5 That one's easy enough. Now, I don't know about you, but I always lost some kind of credit for not labeling something properly when I was a student in a math class. Labels are the most important thing when it comes to creating a graph, whether it's a label of the scale or a label of the values that are plotted, because you can't pull any information from a graph unless you have some labels that tell you what the graph is really dealing with. All right. So here it's pretty obvious, but it's not a bad habit to get into. So you're going to count the boxes or the tick marks and make sure that you're at the right location, because if it's going by 2s or 5s or something like that, you could have a problem. But we're looking at, and I'll label it up here, well, we're going from 45 to 50. So 46, 47, 48, 49. So it makes sense that I would put the 1.46 here. All right. So now we have a follow-up question for the first time. What is the relationship between the two numbers and how do you know? All right. So here I know, just based on what I see, that 1 5/10 is greater than 1.46. You might have gone the other way and said 1.46 is less than 1 5/10. That's perfectly fine, means the same thing. All right, but you can draw that conclusion. Now I put the little boxes there because I was feeling my oats. You know, I was like, I can make a couple of boxes. I'll throw them in there. But the bottom line is, any expression, statement, whatever that gets that idea across is going to be fine. You could have just said 1 5/10 is more than 1.46, and you would have been perfectly fine. And so that's what you want to encourage your students to do when you're formally addressing notation and terminology. Different story. But when you're just driving at the content, the concept, underlying theory behind something, let them write it any way they want, right? As long as it makes sense. So how do you know? Now that's the key ingredient. That's a big takeaway from a number line type question, right? So the further a number is to the right, because numbers always increase as they go to the right, right, on a number line. So in a number line, I'll just jot it down up here. In a number line, larger values are to the right. Now we'll get into negatives next time, but it's a general rule of thumb, and it works in all cases. So that rule, that theory behind this whole thing actually ends up being the explanation, right? So 1.5 is to the right. Actually, it was 1 5/10 is the way they wrote it, wherever they are. Is to the right of 1.46 on the or a number line, doesn't matter. Number line. You know, and that's really what it comes down to. You know, like, can you take that away from the example? Because, you know, graphing on a line, it's like, okay, cool, I demonstrated your skill. But what was the value in that skill, right? So the following little table there. In the one example below, we hit on several different mathematical skills and concepts. Name 3 skills that are demonstrated in this example and evaluate the importance of each one. Well, we have comparing values, and listen, I don't have like a bank of skills to draw from here. Like, I mean, I could put one together, but that's like all K through 8 at least, you know. So, and well, this course really only focused on K through 3 or 4, but it's a lot of skills. So what we do is we just kind of look at it and use our common sense. What did we do? We compared values. We plotted points. So compared values. Plot points on a number line. Points, no, points. And there may be more than 3 skills. We're just only focusing on 3 of them. Just to keep it brief, I'll say convert decimal to fraction form, vice versa. So in this case, we want fraction to decimal. So convert between decimal and fraction. Now, again, that one example, it was a 2-parter, all right, so I'll give you that, but that one example hit on at least these 3 concepts. Now, in terms of their importance, plotting points on a number line. You know, you look at the different possibilities here. Cannot move on without it, and I mean, like, you can't even start the next topic without having mastered this one. Well, I suppose it depends on what the next topic is. Now, if I tell you the next topic is going to involve negative numbers, right? Because we focused on whole numbers and decimals. Now we're going to throw some negatives in there. I'm going to tell you that if you can't compare values, I don't see how you're moving on to the next topic. There's no way you're going to understand how negatives fit into anything. Plotting points on a number line. Now that skill, it's a great skill, but there are other ways to compare values. If I'm saying that the comparison of values is the skill that you just can't live without, then it's possible that plotting points on a line is also along, you know, it has that same sort of severity. But can I still compare the value of numbers without plotting it on a line? I think so, because earlier when we were adding 5 and 7, I did it with a number line, and then we did it with a circle drawing. So, you know, grouping it by 10. So I think we can still develop comparison between values. I mean, I know we can. I'm just kind of playing it here, but you know, like we can still compare values without a number line. It would be great to have it, but it's not 100% critical. So you can move on without it, but I think you're better off if you know it. So I think that's this category. All right. And like I'm really kind of elucidating on the reasoning here, but we'll kind of streamline it in a minute. Convert between decimal and fraction. Well, the next topic is negative numbers. Can we survive? This one, well, let's say you have no idea what negative numbers are about. Now I'm talking about negative whole numbers, so we're just focusing on integers. So we're not even getting into the fraction and decimal stuff for as they apply to negatives, at least not in a significant way. So you could either go halfway between these two. I would lean towards halfway. Or you could just go straight for the can move on. It won't impact the ability to learn the next unit, next topic. Now, 2 topics down the line, you might be screwed, but the next topic, you'll be okay. All right. So incorporating negative numbers will require, poor quality will solid understanding of comparison. And again, you could come up with rationales for just about anything. Your rationale could take any form. The fact is that you should be trying to really consider, all right, what's the important stuff in the unit, and what's the stuff that, okay, I'm not gonna beat it to death if it's not that important. All right, it can move on, but the ability, but will impact ability to learn the next topic, the number line. So the reason here is not necessary to understand negatives, but would be helpful. All right. So these first two categories, they kind of fall into the realm of remediation. So if I'm looking at that first one, the comparison of values, can't move on without it, I'm really hitting that hard in my lesson planning. Right? I'm going after that one. Example after example, tying it into the real world, hitting on the three modes of learning. So the graphical, or sorry, the visual, the verbal, and the computational. And also just coming back to that idea over and over and over again, because that's how important it is. The second one, we can move on. We'll move on to the next topic, but I'm pulling the kids aside that are struggling with plotting points on a number line to remediate them, because yeah, it's not necessary, but it would be helpful. And if it's helpful, then that could make them a better student. All right. Now, the converting between decimal and fractions, that's also, like if a student's weak in that area, that's also an area for remediation, but you got time. All right. So you have time to master this concept before it becomes relevant again. All right. So whenever you make a lesson, are you going to make a table that goes with the level of importance and all the topics that you're going to have? Of course not. What you're going to do is you're going to at least consider these things when developing your lesson. Otherwise, all you're doing is creating worksheets, busy work. Well, we used to call them worksheet days. That's when you just didn't feel like teaching that day. It's like, all right, what do we got in the old workbook there? All right, photocopy 30 pages of that and just hand them out. All right, quietly work at your desk. I'll collect it at the end of the period. Like, yeah, we all have our off days, but that's not really what we're going for here. You know, what we're looking for is a meaningful and useful usefully structured lesson. All right, so that's the moral of the story, and that's ongoing. That's always going to be the moral of the story. All right, so next class we're going to pick up with negative numbers, and you can see, I mean, yeah, there's some decimals in there, but it's not like the be all end all. So number lines, yeah, but again, not the end of the world if the number line didn't really translate, you know, from the student standpoint. All right, so I'm going to stop the recording.